Good. Well, welcome to the first colloquium of the semester. It's my great pleasure to introduce Sandro Tacchella. Sandro was a PhD student at ETH, and after that he came here as a CFA fellow. From there he moved on to UNIST in Korea for a year as an assistant professor and is now at the University of Cambridge in the Kavli Institute of Cosmology. Sandro's research covers observations and theory of the evolution of galaxies from their dawn until the present day. And he's going to tell us about work he's been doing with JWST and some early results from there. So, thank you, Sandro.
Thank you, Ben. Thank you very much for a very kind introduction. And it's really a great pleasure to be back here at the CFA, where I really spent 4 years and some of the basically the 4 best years of my scientific life till now. So it's really nice to see many of you again. And yeah, thank you very much for the time of the past. So today I will be talking to you about some of the deepest images we have taken of the space till date, and focusing really kind of on understanding how star formation took place in the very first galaxies, and also how this can be connected to kind of what we see in today's universe. But before doing that, I want to go in further back in time, actually to the cosmic microwave background. You can see here, this is basically a map from the Planck satellite that shows you, to first order, basically the initial conditions for galaxy evolution and formation. And our standard cosmological model, the lambda CDM, fits this data actually very, very well. And so we can say that to first order, we have a very good understanding of the initial conditions for galaxies. And so if we assume now, that the universe just consists of dark matter, what we can do is actually we can run n-body simulations and, predict how the matter is distributed in the local universe. And so this shows you the cosmic web as predicted from the Millennium Simulation projects, but there have been, of course, many other projects along those lines also in the recent years. And what you can see is that, the matter is very clustered, right? We have, overdensities, we have clusters, we have groups, we have filaments. And the confirmation of the standard cosmological model, again, you can see here on the right, where you see that the large-scale structure of the universe as done by the redshift surveys, including the CFA redshift survey. You can see that this clustering is very similar to what we observe, what we actually predict in these n-body simulations. So everything looks great. But then when you start thinking about galaxies and trying to understand what actually is going on in galaxies themselves, you can see that galaxies are actually sitting in the very centers of these dark matter halos. And there's enormous spatial scales that are involved, right? We have the cosmic web basically on gigaparsec scales. Then we have individual dark matter halos that are on megaparsec scales. And galaxies are actually quite tiny and sitting in the very centers of these dark matter halos of a few kiloparsecs in size. And then for the evolution of galaxies, of course, dark-scale structure matters. It matters whether a galaxy is born in a highly overdensity region or, basically alone in the underdense region of the universe. But then there are also internal processes related to galaxies, including star formation, the formation and evolution of black holes. And what I've put here together are just a few of the interesting physical phenomena that we can observe, or at least think we can observe, and also that are important for the evolution of galaxies, starting out with kind of small-scale processes that are coupled to large-scale processes, such as supernova explosions, black hole feedback, and then we have, of course, the hydrodynamical, kind of surrounding of the galaxy, and gas cooling, gas flows, and so on. And so, not surprisingly, is that when we think about how we have to connect the dark universe, dark matter, to galaxies, it's a bit more complicated. So the first order, we can say, well, okay, as a fiducial paradigm of galaxy formation, we have these tiny fluctuations in the early universe that are growing, and so at some point the baryons, they start to cool and follow basically the dark matter and cool and form stars. But it's kind of obvious that you have to have some kind of regulation process of the star formation. And this you can see quite nicely if you compare the halo mass function to the galaxy stellar mass function. So here, the dark matter halo mass function, so basically number densities of dark matter halos as a function of mass, has been rescaled by the baryon fraction. So here you assume basically that all the baryons cool and form stars. And so this would be the number density distribution of such objects. And then you compare this with the galaxy number density distribution, the local universe, and you can see that both in low halo mass and at high halo masses, you somehow need to suppress the star formation activity so that you're reproducing the galaxy stellar mass function. And so we think that the first order stellar feedback is responsible for regulating the growth at low masses, and at high masses you need something a bit more extreme, which is related to the black hole feedback or HEN feedback. And you can see this quite nicely also when you look at the color distribution. So this is now U minus R color as a function of stellar mass. And the color here is thus corrected. So the first order, what you can see is H or star formation. So here, up here, we have the red sequence. These are basically galaxies that have no star formation, and we have the blue cloud. And if you think about this, right, the most massive halos are the halos that formed most recently. And so what you need to do is you need to kind of, invert, basically need to break this, right? You need to somehow suppress very actively the formation of galaxies at this high mass and to make them all red and quiescent. And so again, this is very consistent with this idea that you need to suppress star formation and galaxy growth at the high mass end. Okay, so how can we learn more about galaxies through observations? Well, we can use, of course, very powerful telescopes. Here is the Very Large Telescope in Chile, but also space-based telescopes, such as the Hubble telescope. And by looking at objects that are further and further away, we can, of course, learn about how the universe looked like, further and further in the past. So that's great. So we can do this, and we can start out mapping physical quantities, such as, for example, the star formation rate density. So this tells you how many stars are forming per co-moving volume, and you're going back in time, right? You go to higher and higher redshifts, and you have up here basically the same corresponding, look-back time, going from basically 0 up to, the Big Bang, all to the right. And so what you can see is that the cosmic star formation at density actually peaks around the redshift of 2. So there was, many more stars formed in a co-moving volume in the past. And the peak happens around the redshift of 1 to 3, so about the look-back time of 10 gigayears or 10 billion years. And then again, the cosmic star formation at density was basically decreasing at earlier times. And so we can divide up the cosmic time very roughly into cosmic dawn, or basically the dark ages after recombination. We have cosmic dawn, where the first stars and galaxies start forming. They then initiated what we call the ionization epoch, which means that we started out with a neutral universe here and end up with an ionized universe here. So we had to have some sources that reionized the universe. And then we had the peak, where most of the stellar mass in the universe formed, which we call the cosmic noon. And then we had kind of a depressing area where less and less stars are forming. Now, important when I show you such diagrams is that actually to see that here we are not looking at the evolution of an individual galaxy, right? So what you're looking here is at the co-moving volume, basically. So we're looking at all galaxies. And so it's actually very, very difficult to form such diagrams and to directly infer what actually the evolution is of an individual galaxy. So at each epoch, we are looking at galaxies, but these galaxies are actually not directly related to each other. And so this is, I think, a fundamental limitation that we have when we look at galaxies at different epochs. So there are still a lot of very fundamental questions that are open related to how galaxies are actually growing, how they're regulating their star formation, about the morphology of galaxies, how galaxies actually build up their elements, which sources in the universe actually reionized the universe, how the first stars in black holes are actually forming in the early universe, and how they then evolved to lower redshifts. So today I will be focusing mostly on these galaxies, though I'm also very excited and happy to talk about those topics. But I try to focus my talk on a few topics so that I'm not bombarding you with too much information. So if you think about going back to the simple dark matter only universe and adding baryons to it, we can think of this very simple modeling where we basically try to understand, well, how do we have to distribute the star formation in these different dark matter halos, right? We take basically the bottom-up scenario with cold dark matter, growing as a function of time. The question is, how do we need to populate star formation in those halos? And so when you look at these simple regulator models where you have somehow a gas reservoir and some of this gas is turning into stars, the star formation rate then also drives outflows. You can do first order write an equation where you say, well, the star formation rate in a galaxy is actually given by how much matter accretes to this galaxy. And so you can come up with this simple equation where you say the star formation rate of a galaxy, a galaxy just a given halo mass at a given redshift, is equal to some form of a star formation efficiency times the baryon fraction times the dark matter accretion rate. So this is like to first order, like one of the most simple models you can come up with. So again, a strong assumption here is that the star formation efficiency, for example, is not redshift dependent. It's just depending on mass, on halo mass specifically. And then you just have basically the amount of fuel that is inflowing into the galaxy. And so you can, use here simple extended projector formalisms or n-body simulations. And for star formation efficiency in such a model, you basically need to kind of compare these two observations. And what we usually do here is, for example, calibrate this with the UV luminosity function at redshift 4. And what you find is, typically that the star formation efficiency here peaks around the halo mass around 10 to the 11 and decreases both towards higher and lower halo masses. And again, this makes sense when you think about comparing this with the stellar mass and the halo mass function. It's basically the same kind of effect. And so if you do this, if you calibrate now such a model at redshift 4, and you just say, well, let's just look at the number density evolution of halos and their accretion rates, you see that such a model is very well able to reproduce basically all the observational data for the cosmic star formation rate density that we obtained pre-JWST, so mostly HSD-related data sets. And what you can see is that going from redshift 4 to even earlier times, so into the cosmic dawn epoch, there's a really strong drop in the cosmic star formation rate density. And so now, because the model is so simple, you can quite naturally understand why that's the case, right? You have here again the star formation efficiency as a function of halo mass. What I plot now, in addition, is the number densities of halos. And so you can see how this basically looks. You can see that from redshift 10, where the halo mass function is very, very steep, right? You can just see here by changing basically a factor of 3, you're changing several orders of magnitude in number density. You're moving to redshift 4, where now the halo mass function is very nice in this regime where we have a lot of efficient star formation. So this strong increase in the star formation density in the universe can be first order explained by the higher number density of objects that are hosting star formation efficiently, but also the higher accretion rates that we have. So now, this is not the only model, obviously. There are many other models. And so you can see, for example, another very popular model is the universe machine, Berusi's model. And you can see that those models reproduce the data quite well as well at lower redshifts. And then there is a very strong difference at redshift, above redshift 10, basically. And the main reason there is that in such a model, the star formation efficiency increases towards higher redshift. And so you're producing, at higher redshifts, more star formation because you have the star formation efficiency that increases towards earlier times. And so, of course, the question is, how do galaxies look there? And so let's move back to observations. And the question, of course, how we are actually able to find such galaxies. So here, imaging is really very fundamental, right? Because these galaxies are actually rare. And so what happens, or what we do usually, is we're using the so-called dropout technique, where we can basically find that the high neutral fraction in the intergalactic medium is absorbing all the photons short-order off the redshifted Lyman alpha line. And so what you see is basically that such a galaxy, now this is a galaxy that was supposed to be around redshift 11, GNC 11, I will be talking more about this object. You can see that it's nicely detected, at 1.6 micron. And at 1.4, you can maybe guess that it's still there, but then at 1.2, it's already not there anymore. And then in all the other bands, it's not there. So it's a nice Lyman break, basically. And so we can determine, based on photometry, quite well how distant such a galaxy is. And then, of course, you want to have other bands and longer wavelengths. And there you can see the challenge before we had JWST, right? Because you have something from the ground, like a K-band, and then you had Spitzer data, IROC. And these data can provide reliable fluxes, but the spatial resolution is quite difficult. I should be careful not, but what you can see basically here, it's very difficult to tell apart of how much light actually comes from this redshift 2 galaxy versus this redshift 11 galaxy. And so then JWST came along, and I'm sure you have heard a lot about this. There are four major science instruments: NIRCam, main imager, NIRSpec, spectroscopy, MIRI extending further into the infrared, NIRIS, which is a slitless spectrograph. And when I joined the CFA, I was able to join the NIRCam science team, and in particular the exgalactic part that was led by, is led by Daniel Eisenstein here. So why is JWST cool, right? There are several different reasons. First of all, it has a larger mirror, so you can collect more light. But more importantly, in particular, thinking about the highest redshift universe, we are extending now much further into the infrared at high spatial resolution. And as you will see, the most crucial part is actually spectroscopy. It's really the first spectrograph in space in the near infrared. And it's really a major step forward, right? Like we're talking here of sensitivity increase, for factor of about 3,000 in comparison to what we had previously with HSD GRISM and so on. So this means like really the discovery space, there is actually huge. So the next few slides we'll be talking mostly about the JADE survey, and I'm not sure how much you have heard about this. Sometimes, people, even though there's a lot of science to be done at a certain place, it's not that much talked about. So I just want to mention here that JADE stands for JWST Advanced Deep Extragalactic Survey, which is really building on both the near-cam and near-spec science teams. The idea is that you really want to get out most of it both from the imaging side and the spectroscopy side, right? You need both. You need to have imaging to actually identify the interesting objects for which you want to get spectroscopy, and you need spectroscopy to characterize those galaxies in more detail, as you will see. And so this is really, a very large survey. It's based on the GTO time, so we have over 800 hours in prime and parallel. And it really, lays the foundation for, as you will see, the early universe science, I think, in the upcoming years. And so again, there's a large team of people involved. Actually, many people are here as well, in particular, Daniel, Ben, but then because we have the JADES collaboration meeting starting out from tomorrow, we have also other JADES members here in the room. So the main areas that we are covering are in Goods South and Goods North, and it's a bit of a complicated layout. You might say, like, Sandro, why is it so complicated? And I say, well, Daniel has designed larger fits. But the reason why it looks a bit difficult is because you wanted to do imaging first, right, and then basically turn around and do the spectroscopy, and then the imaging in parallel again. So there is a lot of parallel optimization so that we can really get most of the data out in every minute of telescope time. And what you can see here are the different depths, basically, that we achieve in different areas. I don't want to go into too much detail, but you can see basically that in our deepest area, we're extending basically the Hubble Ultra Deep Field, much further into the infrared, and even go slightly deeper. And again, there's a lot of very deep spectroscopy. And importantly, we have released a lot of data around the Hubble Ultra Deep Field, around this red region that you can see here. It's all publicly available, also value-added catalog. So if you have not done so, please look at the data, and in particular at the website, where we have a nice viewer where you can scroll around the data and actually see the images of the galaxies and click on them and see the spectroscopy. It's really nice. So again, here we are. This is one of the images in the Good South region, and this image now is at 1, 2, and 4 micron. And we can zoom in on just a smaller area here. This is now a few arc seconds across. And it's just mind-boggling to see, the diversity of galaxies. Everywhere you go and scroll, you can see, objects that look different from each other. And it's just very beautiful. Some comparisons with previous data sets. So this here shows you basically a galaxy at around redshift of 2, slightly above redshift 2. And it's hardly visible in the I band with HSD. And then when we look at this now at with our JADES data at 1, 2, and 4 micron, you can see that this is basically a grand science spiral galaxy, above a redshift of 2. It's really amazing. And we can, of course, also go deep, right? So this is the Hubble Ultra Deep Field. This shows you basically the deepest HSD image, and this shows you at the same wavelength, basically the JADES image of this region. And the first thing is, of course, to see the spatial resolution. So there is a spatial resolution increase when you go to JWST. You can start seeing really kind of in these redshift 1, 2 galaxies, the individual star-forming regions. And then, of course, the background is much smoother, and you are able to pick up the really faint galaxies to much higher signal-to-noise. And again, importantly, we have spectra. They come in different resolution and wavelength grids, basically. So you can see here, this is showing the prism data. So here you can just see the suite of emission lines we can get now very easily at redshifts 4 and 5. And then again, when we go to high-resolution spectra, we can also start seeing broader components, which are indicative of outflows and AGN activity, as we will highlight in a few slides. So one main reason why JWST built was, again, to find some of these highest redshift galaxies. And last year, around this time, we were looking at the first images that we were able to take. And at that time, there was a bit of a small gap of a few days where we were able to actually select high redshift galaxies and put them into slits for a spectroscopic follow-up. And so here, these two galaxies have been high redshift galaxy candidates already with HSD, but those two galaxies were the first time discovered with us in the near-cam data. And so we have been able to put on slits and then get spectroscopy for those. And these are basically the press release spectra, so they don't look that convincing. But here, these are the real data, the real spectra for those galaxies. And to first, maybe you might be disappointed, say, like, well, no, Sandro, I don't see the emission lines and so on. But if you actually look at what you would expect, you actually don't expect to see very strong emission lines at these resolutions and at these luminosities. What you can see here, maybe it's hard to see, these are, this is 10 to the minus 21 ergs per second per centimeter squared per angstrom, right? So we are really pushing to very, very, faint limits here. And so the main feature you're picking up for these galaxies is actually the Lyman break again. So you can see a very strong break. And what we find is that these galaxies, the spectroscopic redshift now determined from these spectra is consistent with the photometric redshift estimates. But because now we know how distant those galaxies are, we are able to measure their cell population properties quite well. The uncertainties are large, as you see, but we have a rough estimate of the stellar masses, the star formation rates, and the ages of the stars in those galaxies. And so what we find is that these 4 spectroscopically confirmed galaxies have stellar masses of the order of 10 to the 8, 10 to the 9 solar masses, and star formation rates of about 1 to 2 solar masses per year. So again, this is actually, when you think about the star formation, very similar to what we see in Milky Way-like galaxies. And given these masses now, you can look at the specific star formation or the mass doubling timescale, and you see that these galaxies are roughly doubling their stellar mass every few tens of millions of years. And overall, this is not crazy. This is very consistent with what you expect from simple lambda CDM cosmological models, simple simulations or analytical models. As you can see, these images, these galaxies are actually very compact, and some of them are so compact that it's actually hard to infer an accurate size. So we find that these galaxies have rough sizes of a few tens up to maybe 160 parsecs. So these galaxies are very compact, which then implies, of course, even though the star formation rate is low, the star formation surface densities are actually extremely high, right? So these galaxies are very dense, growing very, very rapidly in a very small region of the space. So let me move on to GNZ11, which I just mentioned, as an example before, as of a high redshift galaxy dropout. It's actually interesting to go back in time a little bit, because in 2010, Richard Bounds actually already found this galaxy in the NICMOS data at that time. And he commented in the paper that, well, we cannot really rule out it's a high redshift galaxy, but they think it's highly unlikely. It's probably a transit or a spurious source because it's so bright, right? It was visible in the NICMOS data, like, is it really a redshift 9 galaxy? But then with better data, in particular with IRAC at that time and the K-band and an additional 1.4 micron image with HSD, Pascal Rouge put it back onto a high redshift galaxy candidate list, at that time inferring a photometric redshift of 10, and then using GRISM to basically, taking this as a break and inferring a GRISM redshift of 11. And so if you look at this now, this shows you the absolute magnitude in the UV as a function of redshift. These are basically all the photometric redshift galaxies, and these are the spectroscopically confirmed galaxy. And what you see is GNZ11 lies here, right? It's a real outlier both in redshift but also in magnitude space. So it's extremely high. It's about 3 times L star of redshift 7. Okay, so why is it so bright? Is the distance wrong? Is something else going on with the emission? Is it an AGN? And so this object is actually, as the name says, GN, like Goods North. It lies in Goods North. And so we got a lot of nice imaging data and also spectroscopy for this object. And I've actually written a suite of papers. In particular, it seems like most of the first authors here are all in the UK. I don't know, but it's an interesting object to understand from the environment perspective, from the morphology perspective, from the emission line ratios that we'll see, and also possible population 3 signatures in the halo. So I'll focus on a few of these aspects. First of all, the spectrum. That is, of course, much more convincing than the redshift 10 and above galaxies that I showed you. But again, this is a really bright galaxy, so no surprise that we have a much higher signal-to-noise spectra. You can now start seeing really a lot of individual emission lines, and again a very sharp break around Lyman alpha. And the redshift here is 10.6 now, so that's confirmed. When we look at the photometry, you might say, well, okay, that's pretty boring now, right? You can see it's quite compact and it's a nice dropout, but what can we learn? Well, if you look at the morphology a bit more in detail, you can start seeing interesting substructures. So first of all, let me not advance. Here, what we have some extra emission, which we call the haze, and it's not very clear whether this is actually associated to the galaxy or whether this is a foreground or background galaxy. But when we look at the central region of this galaxy of GNZ11, we can actually see that it's slightly extended. Okay, so it is extending beyond the point spread function. And what we can do now is we can forward model the light and basically try to assess how important is kind of a central point source-like component versus kind of the extended galaxy component. And we use here the code ForceFlow that Penn Johnson here has been developing over the last few years, which is really cool because it allows you to basically forward model not just the data on the mosaic level, but actually on the individual exposure level. And this is very important, right? Because you really want to get most of the data, most of the information out of the data. When you combine everything into a mosaic, you're by definition, you always destroy information because you are combining it onto a new pixel grid. And so you really want to work with the individual exposure to get most out of the spatial resolution we can obtain with JWST. And so what we can then do is basically we can look at the point source SED at the flux distribution of the point source and the flux distribution of the extended component. And what we have in JADES is we have these additional medium bands which are actually very useful to understand the strength of possible breaks and emission line contributions. And so what we can then do is we can then model with different, with different stellar emission templates. Basically, we use the code called Prospector. That you can have flexible star formation histories, dust attenuation, and so on, to then basically forward model the photometry both for the point source and the extended source to understand what is the source of the emission. Again, here I'm just assuming everything is stellar emission, processed by dust and by gas. But there is no HEN contribution here. And actually, you can reproduce both the point source and the extended source quite well. What we find is that the point source has a kind of a strongly increasing star formation history, is quite young and rather low in mass of the order of 10 to the 8.4. On the other hand, the extended source is slightly older, maybe a constant or slightly decreasing star formation history with a stellar mass of nearly 10 to the 9. Okay. So now if you look at the luminosities, you can clearly see that the point source is dominating the luminosity, but the mass is dominated by the extended component. Okay, this is not the haze, this is just the extended component around the central region. And so, one possible interpretation here is that, because when you look at the spectrum, the first order, you can see that it seems to be quite consistent with star formation as well. Well, it's possible that we just have this nuclear starburst, basically, that is currently outshining the whole galaxy, and you're producing a lot of young stars in the core, and you have kind of a slightly older, underlying disk component. However, when you start looking at the spectrum in more detail, you actually see that there is also an HEN contribution in the central core, and there are different lines of evidence for this. For example, you can look at the P Cygni feature around the C4 line that implies outflow velocities of up to 1,000 kilometers per second. But then also when you look at the ionization state of the semi-forbidden lines that imply very high densities. So you are looking, it seems, at the BLR-like region, in the very central core. And so our current interpretation is that basically the central point source is really, dominated by HEN-like emission, and the galaxy is kind of this more extended component. And so if you use now, the magnesium doublet and the N4 line to infer a black hole mass, you can see that this black hole mass is of the order of about 10 to the 6. And again, this puts the galaxy at redshift 10.6, right? So we are talking here of a galaxy, of a black hole that sits around here. And so if you would grow such a black hole with just Eddington accretion, right, you would end up with something that's actually consistent with black hole masses of 10, of 10 to the 9 at redshift 6. So with kind of, the brightest quasars that we observe. And you can also start thinking of where does this black hole actually start growing from, right? If you think about Eddington accretion, you need to have rather massive seeds. If you are able to grow super Eddington, then you are more in a regime where you can also include stellar remnants. Now, this is not the only galaxy. We can start looking actually more, throughout the whole JADES data sets, right? So we can look at basically broad line regions based on, looking at broad components in the Balmer lines, but no broad components, for example, in the metal lines like oxygen 3, so that, we rule out basically outflows. And so if we do this, we find consistently black hole masses of the order of 10 to the 6, 10 to the 7, 10 to the 8. And if you now look at the simple scaling laws, for example, for the black hole mass versus stellar mass, you can see that those black holes mostly sit up here. So given the stellar mass, they lie above the local relations for what we would expect for local black holes. So they are kind of have rather massive black holes given their stellar mass. But when we look at, for example, the dynamical mass, they seem to be in better agreement, at least for those objects where we can kind of roughly estimate the dynamical mass. Most of when we look at the images, these HENs look very compact, they're very red. But it's actually very difficult to find them otherwise. When we look at, for example, BPT-like diagrams, for example, here just the standard BPT diagram, these galaxies with these black holes lie actually kind of, consistent with local star-forming galaxies. And this is not too surprising, right? Because, the metallicity is expected to be much lower at these redshifts. And so you would expect that there is a tendency of, AGNs moving kind of more in this regime here. So standard BPT diagrams will not select these broad line regions of AGNs. Now, not everything that is a red point source is actually an AGN. That's another interesting comment to make. What we see is actually, we see also a lot of brown dwarfs, and they are actually quite similar to AGN-like spectra. So you see basically kind of, this kind of bluish color, but then a very strong red peak. And one way to identify them is, of course, through the SEDs and medium bands spectra. But you can also look at proper motions, and because we have this deep HST imaging, we can actually do this nice comparison between the HST and the JWST data and see how these, these point sources actually move around in the images, which helps to identify them as well. Okay, so I have focused now on a very few galaxies, right, at redshift 10 and above. I focus now a bit more on like what is the general population of galaxies. So we had, in the literature, the first constraints, I think a few days after the first images appeared on the UV luminosity function above redshift 8. And most of these works kind of consistently found that there seem to be many, maybe too many high redshift galaxies. And the question is why? In shades, we have been also starting to look into this. What shows you here, this is the first order, the UV magnitude versus redshift, and this is what we had before JWST. And now this is basically the number of objects that we roughly find of the order of 700 in shades and at high redshifts. And you see here, these are the black points. Okay, these are the ones that I talked to you before. These are the spectroscopically confirmed objects. Now these are only photometrically selected. Okay, these are candidates, so we have to be kind of careful of not overinterpreting what we find here. But our goal is, of course, to spectroscopically follow up as many as we can, but it's actually quite difficult. So I will not show you a complete list next year. It takes many years to follow up most of them. Myself, I'm mostly interested to understand the morphology of those galaxies, and it's interesting because some of the high structure galaxies are very compact, but it's not all that they're not all compact actually. You can start seeing extended structures. So some of these are actually spectroscopically already confirmed here. And what you can see, it reminds me a little bit of the HST time where we saw that the UV is kind of clumpy, but when you go to longer wavelengths or terrestrial optical, you can start seeing kind of a more compact configuration. But important here is also to think that PSF effects play a big role, right? We're going here from the blue to the red, and the factor of roughly 4 in the full width half maximum of the PSF. But clearly, these objects are interesting to study morphologically. So are these galaxies breaking or challenging lambda CDM? And I think there are different questions that we can ask. For example, the first one is whether there are too many galaxies at redshift 6, and the other, if their galaxies are too massive above redshift 6, and also whether there are too many bright galaxies. And there are slightly different questions, I think. So thinking about stellar masses, some of the first stellar mass measurements of galaxies above redshift 6 came out very high, right? A few times 10 to the 11 solar masses. And what is shown here is work that we have done together with Chris Lovell to understand actually, if you look at the sky with a certain volume, what is the most massive object you would expect to see? Okay, and basically this dashed line here is assuming that when you look at a typical volume and look at the halos, basically you form 100% stars. Okay, like a halo forms basically gas, the baryon fraction you form basically all the stars that's possible with the amount of baryons. And you can see that these galaxies basically lie on or above this line, but what is really expected from simple galaxy evolution models or from things such as illustris is something more along these lines, right? So they are several sigmas above this line already and really kind of pushing the limit here. So what's going on? Well, actually, when you start thinking about the problem, possible systematics is, of course, these were only photometrically selected. And this object here, we know already is a low redshift galaxy. So this actually moved to redshift 4.6. So it moved all down here to the left. And also here, these are only photometrically selected objects. So we have to really get spectroscopy to confirm their distances. Then one other caveat, of course, is that we assume when we measure these stellar masses that all this emission is from stars. But again, as I showed you in the case of GNC 11, it's actually very difficult to see the AGN. It took us a few months to really come to that conclusion. And so it's very possible that some of this emission is actually dominated or at least contributed by an AGN. Bursty star formation can be important because, as I mentioned very briefly, outshining can be important. So assuming, depending on what exactly you assume for the star formation history, you can actually bias your stellar mass estimate quite significantly. So if you're going through a burst and you assume a constant star formation, you might overestimate the stellar mass by a significant amount. And then, of course, there are questions about the stellar populations. Should we think about variation in the IMF first before we, challenge the cosmological model? Binarity fractions that might also change towards higher redshifts and so on. Then the other question about whether there are too many bright galaxies above redshift 10 is something that we have been starting to think as well as, with Jacob Shen, who we have been now trying to take the simple model I started out with, trying to make it slightly more complicated by just introducing a term with scatter, right? So before I basically showed you of how we convert the halo mass function to a star formation rate and the UV luminosity. What we can do is we can assume that there is more scatter in that relation. And this scatter could be related to the burstiness of star formation, all right? But it could also be related to, for example, variations in metallicity, variations in dust, and so on. So we basically have a scatter term that changes the correlation between the halo mass and the UV luminosity. So you can have different terms that contribute to this scatter. And so what we find is, not too surprising because the halo mass function is so steep. If you introduce scatter, you're scattering, more probably up, right? So you can produce from, in the tail of the distribution, you can, produce very rare but very bright galaxies with enough scatter. And so what we find is that if you just vary the scatter as a function of redshift, okay, so sorry, maybe I should explain first that if you introduce the scatter now, and you increase the scatter, you can go from this yellow to this, red lines. And what you can see is you can just boost the cosmic star formation rate density or the UV luminosity density. And so if we now assume a scatter that evolves with redshift, you can come up with this blue line that very naturally fits the data. So one possible outcome is, before breaking the cosmological model, you can actually just change the conversion going from these halo masses to the UV luminosity, and you can very naturally reproduce the UV luminosity function density at high redshifts. Now, just to highlight, Diana Kimi, actually, she was an undergraduate here working with Sonak Bose and me at that time. We have been exactly trying to understand how well can we actually try to learn more about different dark matter models from JWST observations. And so what we find at that time, we have looked into a simple warm dark matter model and a cold dark matter model, and just changing the star formation efficiency, by boosting basically the low mass end in the star formation efficiency from a low to a higher value. And what you can see here is that there is this very nice degeneracy between having a warm dark matter model and increasing the star formation efficiency versus, a cold dark matter model and lowering the star formation efficiency. So again, it's very difficult, I think, to learn about cosmology and the dark matter model as long as we don't have a full understanding of the baryonic physics. So now I'm switching gear, and I have probably another 5-10 minutes, yes? Okay, so I'll move more into the structure of galaxies and the morphology. It's not too surprising, morphology for galaxies is important, right? Because you learn a lot about, mergers, angular momentum of the gas, and star formation in galaxies. So I myself have been working a lot on redshift 2 galaxies, actually. So before I came here, I worked a lot with ground-based IFU data on the Symphony side and, correlated this with Hubble data to map out the stellar mass and the star formation distribution and understand how this links to the kinematics in these galaxies. And so now we can, of course, push this to higher redshifts because with JWST we were able to probe actually the rest frame morphology of galaxies out to redshifts of 8 and 9. And so I want to show you here basically this very interesting case of a spectroscopically confirmed galaxy at redshift 7.43 in the JADES data. So now we are basically 700 million years after the Big Bang. Okay, so we basically are not anymore kind of at redshift 10, but slightly kind of closer, where we can probe the rest frame optical side of things. And we are finding that this galaxy has a stellar mass of about 10 to the 8, and the star formation of about 10 solar masses per year. So kind of typical star-forming galaxy at this epoch. And the interesting part that we find is that it has kind of an interesting color gradient. So this is now color gradients as a function of radius here where the colors or the fluxes have been convolved to the same PSF. So what you see here is not PSF effects, but just really color gradients in Galaxy. And you can see that, in one color, in the 3.5 versus minus 4.1 color, this goes up and the other one goes down, which indicates that, there is a 410M micron, 4.1 micron excess when you go to the outskirts, which, with the spectrum, you can clearly see is related to the oxygen line and the H-beta line. So when we look at the spectrum itself, we don't see any HEN activity, so we just focus here now on stellar emission again. And so the galaxy to first order is quite compact, but has also this clump in the outskirt. And so what we have been doing, again with forced voice decomposing the light, because if you look at the color gradients here, everything is convolved with the point spread function, right? So it's difficult to really learn about the underlying stellar population gradients. And so in order to do this, what we have done is basically we forward model the light with a core profile, a disk profile, and the clump in the outskirts, to understand basically, how much star formation is taking place in the central region versus in the outskirts. And so what we find for the core is, a surge signal of about 2.5, a compact configuration, and then we have a disk-like component